In the mid-1980s, the strategic balance of the Cold War rested on a fragile assumption shared by both superpowers. Nuclear weapons could be counted, mapped, and therefore deterred. Missiles in silos had coordinates. Submarines had patrol zones. Bombers had bases and flight corridors. The logic of deterrence depended on visibility. If you could find the weapon, you could plan to destroy it before it was used. But in the closing years of the Cold War, that assumption began to quietly collapse. In Moscow, Soviet intelligence analysts studying satellite imagery noticed something unsettling across the American Midwest. Hardened missile silos associated with the LGM-118 Peacekeeper program showed irregular activity. Construction had been completed. Thermal baselines had been established. Yet on several confirmed overflights, the expected heat signatures were missing. The silos were intact, guarded, and powered, but empty. No launch preparations. No signs of fueling. Just absence. At first, the anomaly was treated as a calibration error. Optical satellites had limited dwell time. Cloud cover interfered with infrared collection. But the pattern persisted. Missiles that should have been present explained nothing by staying invisible. Signals intelligence offered no clarity. There were no launch warnings. No alert traffic indicating a dispersal under crisis conditions. The missiles had not been fired. They had simply vanished. For Soviet planners, this raised a more dangerous possibility than a technical malfunction. If the missiles were not in their silos, they had been moved. And moving an intercontinental ballistic missile was not a trivial act. A single Peacekeeper weighed nearly 90 metric tons and required extensive infrastructure. Traditionally, relocation meant convoys, reinforced roads, and unmistakable signatures. Yet American rail lines stretched for hundreds of thousands of kilometers, linking military bases to civilian industry in a continuous, high-volume flow of freight. By the early 1980s, the United States Air Force had openly studied survivability concepts for land-based missiles, responding to improvements in Soviet counterforce accuracy. Fixed silos were becoming vulnerable. A mobile basing mode promised survivability through uncertainty. Among several concepts evaluated, rail mobility stood out. The idea was simple in theory and destabilizing in practice. Conceal strategic weapons inside the normal circulation of a civilian rail network so dense that no adversary could track it in real time. Soviet satellites could image individual rail yards, but not the system as a whole. A satellite pass lasted minutes. A train could move kilometers in that window, enter a tunnel, stop beneath industrial cover, or blend into thousands of identical consists. Monitoring required persistent surveillance the Soviets did not possess. The battlefield was no longer a launch site. It was a continent. By the time analysts in Moscow began to connect these facts, the implications were already clear. If American nuclear missiles were moving, then the mathematics of deterrence had changed. Target lists became estimates. Counterforce plans became guesses. And the certainty that once stabilized the nuclear standoff began to dissolve. The challenge facing Soviet intelligence was not simply detection, but discrimination. The American rail network carried millions of freight cars every day. Coal, grain, automobiles, industrial equipment, moving on schedules that shifted constantly. From orbit, a missile train did not announce itself. It did not carry distinctive escorts or travel on restricted lines. It used the same locomotives, the same sidings, and the same junctions as civilian traffic. To the sensors aboard Soviet Zenit optical satellites or radar platforms, it was just another train. This posed a fundamental problem for the KGB and the GRU. Strategic surveillance systems had been designed to watch fixed objects or predictable patrol areas. Rail traffic was neither. Satellites followed known orbital paths and could only observe a given stretch of track for a few minutes per pass. Between those passes, a train could travel tens of kilometers, change direction, or disappear into urban rail yards dense with overlapping lines and rolling stock. No Soviet system could maintain continuous custody of a single train across multiple satellite passes. Compounding the difficulty was American doctrine. The rail-based missile concept was not intended to be permanently deployed across the network in peacetime. Instead, Missiles would remain in secure garrisons during normal conditions and disperse only during heightened alert. This meant there was no constant pattern to observe. Dispersal could occur rapidly, without prior warning, and blend seamlessly into routine rail activity. From the Soviet perspective, the most dangerous moment would be the one they could not see, the hours immediately after dispersal. Efforts to identify technical signatures offered little reassurance. Analysts examined axle counts, car length, and weight distribution, hoping missile cars would betray themselves through non-standard configurations. But American designers anticipated this scrutiny. Missile cars were engineered to conform to standard freight dimensions and axle arrangements, minimizing visible anomalies. Any slight deviations were statistically drowned out by the sheer volume of civilian freight moving at any given time. Electronic intelligence provided no reliable solution either. Rail traffic did not emit the same radar or communication signatures as naval task forces or bomber formations. Secure military communications were tightly controlled and sporadic. A missile train in motion was radio silent by design. There were no radars to track, no transponders to interrogate, no continuous command links to intercept. By the late 1980s, Soviet analysts were forced to confront an uncomfortable conclusion. Tracking mobile missiles on the American rail network was not a matter of improving sensors or refining algorithms. It was a structural impossibility. The rail system itself acted as a shield, overwhelming surveillance with scale and noise. What had once been a finite set of targets had dissolved into a moving field of uncertainty, where the absence of information became the defining threat. As the intelligence picture darkened, Soviet military planners shifted from surveillance to physics. If the missiles could not be reliably tracked, perhaps they could be constrained by the limits of engineering. Rail lines imposed weight limits. Curves generated lateral forces. Bridges and ballast tolerated only so much stress. Somewhere, analysts believed the Americans would have been forced to compromise. A weapon as massive as the Peacekeeper could not simply ride unnoticed on civilian infrastructure without leaving a trace. Soviet engineers calculated load distributions and compared them to known American rail standards. A rail car carrying nearly 90 metric tons, plus protective structures, launch equipment, and crew facilities, should have required reinforced track or unusually heavy bogies. Yet satellite imagery revealed no such modifications. Rail maintenance patterns appeared routine. Ties were replaced with ties. Ballast was replenished at normal intervals. There was no visible effort to strengthen the network along suspected routes. This contradiction drove deeper concern. If the Americans were not reinforcing the tracks, then they had solved the problem internally. That meant advanced suspension systems, hidden load-spreading mechanisms, or structural designs that reduced peak stresses. Each possibility suggested a level of engineering sophistication that exceeded Soviet expectations. It also meant the missile cars could blend physically as well as visually into the rail system, leaving no measurable deformation for satellites to detect. Another assumption fell apart when analysts considered launch requirements. Intercontinental ballistic missiles were not fired casually. A launch demanded precise alignment with the Earth's rotation and gravitational reference frame. Fixed silos achieved this through permanent surveying. Mobile systems traditionally required prepared launch sites. A train stopped on uneven ground, resting on springs and steel wheels, should not have been able to provide the necessary stability. Even minor misalignment could translate into kilometers of error at intercontinental range. Yet American test data, pieced together from open-source reports and limited intercepts, suggested the system was designed to launch from almost any point on the network. That implied a launch method that temporarily converted a rail car into a rigid platform, bypassing the suspension entirely. How this was accomplished was unknown, but its implications were stark. The missile no longer depended on the track for stability. The track was merely a delivery path. By the late 1980s, the Soviet General Staff faced an unwelcome realization. The problem was not that the rail-based missile violated known laws of engineering. It was that American designers had redefined the problem. Mobility was no longer constrained by infrastructure. It was enabled by it. The rail network did not limit the missile. It concealed and protected it. In trying to expose a technical weakness, Soviet analysts instead uncovered a doctrinal one of their own. They were still planning for weapons that stayed put. By this stage, the concern inside Soviet strategic circles had shifted from feasibility to consequences. If the rail-based missile worked as intended, it did more than complicate targeting. It undermined the logic of counterforce strategy itself. Soviet nuclear planning relied on the ability to strike American missiles before they could be launched. That required precise, preloaded coordinates and predictable basing modes. A weapon that could change location continuously rendered those preparations obsolete. The problem was magnified by scale. Even a limited deployment of rail-mobile missiles would force the Soviet Union to account for thousands of kilometers of track. Every junction, siding, and rail yard became a potential launch point. Worse, American planners did not need to deploy large numbers of missiles to achieve this effect. A relatively small force, once mobile and concealed, could absorb a disproportionate amount of Soviet attention and resources. The cost imbalance was unmistakable. Soviet analysts also began to consider deception. A missile train did not need to look unusual to be effective. In fact, its effectiveness depended on being unremarkable. If the United States could field rail cars indistinguishable from civilian freight, it could also field decoys. Empty cars built to the same external specifications would force an adversary to treat every similar train as potentially lethal. In targeting terms, uncertainty multiplied faster than warheads. This had immediate implications for arms control. Verification regimes depended on the ability to count launchers and confirm their locations. Mobile rail systems resisted both. Satellites could not distinguish real missile cars from decoys with confidence. On-site inspections were impractical once trains left their garrisons. From the Soviet perspective, this eroded the foundation of existing and proposed strategic arms agreements. A weapon that could not be reliably counted could not be reliably limited. There was also a political dimension. Rail mobility allowed missiles to move through or near population centers, industrial zones, and critical infrastructure. Striking such targets carried catastrophic civilian risk. Even in a full-scale war, this complicated decision-making. The weapon exploited not just physical concealment, but moral and strategic restraint. Deterrence now depended less on firepower and more on forcing hesitation. By the end of the decade, the Soviet leadership understood that the rail-based missile was not simply another delivery system. It was a strategic lever. It shifted the burden of action onto the adversary, compelling constant surveillance, expanded targeting, and increased spending. Whether the missiles ever launched was almost beside the point. Their existence alone imposed pressure on an already strained system, turning mobility into a form of strategic dominance. As the strategic implications became clearer, Soviet intelligence focused on one remaining hope. That mobility came at the cost of accuracy. For decades, ballistic missile doctrine had treated precision as inseparable from fixed geography. A silo's coordinates were surveyed once and never changed. A submarine's position could be estimated before launch. But a train was different. It vibrated. It braked. Curved. It stopped on uneven ground. Even a small error in launch position or alignment could translate into a miss measured in kilometers at intercontinental range. Soviet ballistic specialists initially took comfort in this assumption. They argued that rail-based missiles, even if survivable, would be imprecise. Suitable for city targets perhaps, but ineffective against hardened military infrastructure. In this view, rail mobility traded accuracy for survivability, preserving deterrence but weakening counterforce capability. That distinction mattered. A weapon that could not reliably destroy silos did not fundamentally alter the balance. That confidence eroded as fragments of technical information accumulated. Open-source American engineering literature, combined with indirect intelligence, pointed toward advances in inertial navigation that challenged Soviet expectations. By the late 1980s, the United States had fielded guidance systems that no longer relied on external references after launch. Instead, they measured motion continuously, integrating acceleration and rotation from the moment a missile began moving. In principle, such a system did not need to know where it was fixed to the Earth. It needed only to know how it had moved. This was deeply unsettling. A missile equipped with a high-quality inertial reference could be transported across thousands of kilometers, subjected to vibration and stops, and still retain an accurate internal record of its position. When brought to launch readiness, it would not need a prepared pad or lengthy alignment. It would already know where it was relative to the planet beneath it. For Soviet planners, this closed the last conceptual gap. Rail mobility no longer implied degraded performance. It meant survivability without sacrificing accuracy. The missile was not compensating for motion. It was indifferent to it. Combined with a cold launch system that minimized stress on the platform, the rail-based missile became a fully credible counterforce weapon. At this point, the concern was no longer technical. It was systemic. The United States had fielded a weapon that could survive a first strike, remain hidden during crisis, and still deliver precise retaliatory blows. Deterrence was no longer anchored to fixed points on a map. It was distributed, mobile, and resilient in ways Soviet doctrine had not anticipated. By the time the Cold War entered its final years, the rail-based missile had achieved its purpose without ever firing a shot. The Soviet leadership now faced a strategic environment defined less by confrontation than by exhaustion. Countering mobile missiles demanded new satellites, expanded analytical capacity, redundant targeting plans, and parallel development of similar systems. Each response carried enormous economic cost. The pressure was cumulative and relentless. The irony was unmistakable. The rail-mobile missile did not need to dominate the battlefield to be effective. Its value lay in forcing the adversary to chase uncertainty. Every kilometer of track became a liability. Every unremarkable freight train became a question mark. Strategic planning, once grounded in known quantities, drifted into probability and guesswork. In that environment, confidence eroded faster than capability. As political change accelerated in Eastern Europe and the Soviet economy weakened, the strategic calculus shifted. The United States, no longer facing a peer competitor with matching resources, reassessed the necessity of the system. With arms reduction talks advancing and the Cold War drawing to a close, the rationale for maintaining rail-based intercontinental missiles diminished. The program was ultimately canceled, its technology shelved or repurposed, its specialized railcars withdrawn from service. Yet the legacy endured. The rail-based missile demonstrated that survivability could be achieved through integration with civilian infrastructure rather than isolation from it. It showed that mobility, when combined with advanced guidance and disciplined doctrine, could undermine traditional concepts of detection and preemption. Most importantly, it revealed how strategic advantage could be gained not through overwhelming force, but by imposing unsustainable demands on an opponent's decision-making and economy. In retrospect, the inability of Soviet satellites to reliably monitor moving nuclear missiles was not a failure of intelligence alone. It was a signal that the character of strategic competition had changed. The battlefield was no longer confined to bases, silos, or patrol zones. It had expanded into the ordinary flow of modern society, where distinction itself became the rarest commodity. If you found this exploration of Cold War strategy and hidden military technology insightful, consider supporting the channel by liking the video and subscribing. Your support helps bring more deeply researched, historically grounded documentaries like this one to life.